So without any delay, we are moving to the next report from an excellent place, an excellent center in Europe, the Leibniz Rechenzentrum, run by Bayerischen Akademie der Wissenschaften. And our speaker is Dr. Herbert Huber, who obtained a PhD in physics from the Ludwig Maximilians University of Munich in 1998. He joined LRZ in the year 1997 and is actually leading the High Performance Systems department. The focus of his work and his research interests are energy-efficient high-performance computer infrastructures, processors and systems architecture, interconnection network, file systems, and supercomputing centers. So here it is Herbert Huber, Head of High Performance Systems Division and Leibniz Supercomputing Center.
So hello, thank you, and sorry for the hiccup. I hope you can hear me now, Olaf.
Yes.
Yeah, good. So I will start. Good. Yeah. As you can see on this slide, the Leibniz Supercomputing Center of the Berlin Academy of Sciences, we have approximately 250 employees, and we are 58 years old. So we were founded in 1962. And LRZ is a computer center for all Munich universities, and we are a regional computer center for the whole state of Bavaria, as well as a national supercomputing center for Germany, and in the PRAISE project, we are a European supercomputing center for all European nations. Yeah, LRZ operates cutting-edge IT infrastructure, starting from email and web services, and we also operate the Munich Scientific Network. We operate large storage systems. We operate a compute cloud, a Linux cluster, and large HPC systems, as well as we do training and consultancy. So the focus of my work and also of LRZ's HPC systems is to improve the energy efficiency. And how do we do that? Okay, we created the 4-pillar model for energy efficient operation of supercomputing centers, as well as all systems operated in our data center. So to reduce, first of all, the first pillar is the building infrastructure pillar. So we have to reduce the losses in the power supply chain, and we have also to exploit all possibilities for free cooling. So compressorless cooling is really a major indicator for efficiency. And we reuse the waste heat of our HPC systems. In winter, we heat our buildings, and in summer, we use a large portion of the waste heat to generate chilled water for the disk systems, which still need chilled water to be cooled. Of course, the HPC system hardware we have to select the most energy efficient supercomputing hardware. So of course, use the newest semiconductor technology, use energy saving processor solutions, and consider using special hardware or accelerators for solving specific scientific tasks or numerical algorithms. And on the software side, on the system software side, you have to monitor the energy consumption or the power consumption of your HPC systems. Otherwise, you cannot improve it. So you have to monitor the power consumed of the HPC systems running normal applications. And we also use energy-aware system software, for example, energy-aware scheduling, where the scheduler selects the most suitable processor frequencies depending on the application which is run on the system. And of course, you have to monitor the performance of the applications. And on the other side, on the application side, you have to improve the performance of the application if the real world application performance is much below much below the LINPACK performance. So if the application performance is only in the order of 1 or 2% of the LINPACK performance, you need to optimize the application. And to do so, you have to use the most efficient algorithms, use the best libraries, and the most efficient programming paradigms. So in order to improve the power needed to operate the system or to cool the system, we use since 2011, we use direct warm water cooling. And that's a very old strategy because the automotive industry uses direct water cooling since decades. And why is this so? It's very simple. The cooling efficiency or the thermal inertia of water compared to air, there's a factor of 300. So water is a factor of 300 more cooling efficient than air. And that's why high power motorcycles and also cars they need to be, or the engine need to be cooled with water. Air is no feasible solution any longer. And as of today, where modern HPC racks or modern systems have a power consumption of more than 50 kilowatt on a per rack basis, also for these solutions, air cooling is not any longer feasible. So LRZ, IBM, and Lenovo, we can call us really pioneers of direct hot water cooling because we use this technology since the year of 2012 for our supercomputers. And on the supercomputer side, we can enhance the inlet water temperature up to 50 degrees Celsius without any CPU being thermally throttled. And the heat removal efficiency of the direct warm water cooling solutions is in the order of 80%. This could still be enhanced, and I will tell you why it's not higher today. It's the next slide. You see the two blades or two nodes of our current supercomputing system. It's the Lenovo ThinkSystem SD650 solution. And everything on these two nodes, every hardware component is direct warm water cooled, except the power supplies, which are sitting here. These power supplies are still air cooled, and that's a problem because it limits the efficiency of the direct warm water cooling solution, because cold air is sucked over hot components, so there is a high percentage of heat transferred to the cooling air, which is only needed for the power supplies. So in future, we really request HPC solutions where all components, also the power supplies, are direct warm water cooled. And then for such solutions, you can thermally isolate the rack. You can just operate like a warm water boiler in your household. It's thermally isolated. No part of the HPC system is still using, or the HPC nodes is still using or needing an airflow any longer. So you can thermally isolate the rack, and the cooling efficiency will be in the order of 97 or 98%. Talking a couple of words for SuperMOOC next generation. The system has 6,480 compute nodes. It has a real peak performance depending on the AVX frequency of 22.9 petaflops. And our Lindbeck number is 19.5 petaflops. Yeah, and it was, yeah, so we had SuperMOOC NG was on rank number 8 in the November 2018 list. Yeah, and we still now, every supercomputing conference we go up, and currently SuperMOOC Next Generation is on rank number 17. The nominal so our CPUs can be operated in two modes. We can operate it in the 240 watt mode and the 205 watt mode. And the default frequencies for these two modes are listed here. It's the nominal frequency for the 240 watt mode of the CPUs is 2.7 gigahertz, 3.1 gigahertz, and for the 205 watt mode it's 2.7 gigahertz. And the peak frequency for the 240 watt mode is 3.9 gigahertz, and for the 205 watt mode 3.7. And I just must tell you that we don't operate the system in normal user mode in the 240 watt mode. We always operate it in the 205 watt mode. I have to speed up a little bit. Yeah. What's special about SuperMOOC Next Generation? Yeah, the cooling, so we use hot liquid cooling with an inlet temperature of up to 50 degrees Celsius. We use energy efficient hardware and we use dynamic frequency scaling in both TDP modes. And an additional specialty is that we use energy-aware scheduling. We only run code which really profits from high CPU frequencies at high CPU frequencies. So normally a code which doesn't profit from 2.7 gigahertz processor frequencies is normally run with 2.2 or 2.3 gigahertz. We reuse the waste heat for our office building and also for chilled water production in summer, because we have a number of absorption chillers connected to the half of the SuperMOOC NG system racks. And the power usage efficiency of our supercomputers is in the order of 1.06, and compared to average computing centers which have a PUE of 1.5 to 2.0, it's really a good number. And all our IT infrastructure in the data center is operated with 100% renewable energies. Just one slide and then I'll stop. The value of direct warm water cooling. Yeah, it reduces the noise in the data center because no fans are running in the nodes. You can use the maximum TDP CPU choice. It will also reduce the server power consumption because you have not to operate fans in the node. And you have also a lower processor power consumption because of the TDP, or the chiplets are running colder. So it's in the order of 15%. And it reduces the cooling power consumption very, very much. So at 40 degrees Celsius inlet temperature, it's a fraction of 15%, which you need less electrical energy to cool the system. And if you also, in addition, use energy-aware scheduling, you also spare or save another 5%. However, conventional chillers are still needed, or chilled water is still needed to cool large disk systems. And these large disk systems of our SuperMOOC Next Generation system is cooled with chilled water generated by absorption chillers. Yeah, in my last slide, you see the cooling towers on the roof of our data center, and we have 6 cooling towers installed. These are wet cooling towers. So you have, we still need quite a large amount of water to operate these towers. So I think my time is over, and so thank you very much, and I hope we have time for some questions.
Thank you, Herbert. We certainly have time for one or so questions. Let me sort of reminisce about visit. If you remember, back in 2013, just 1 year after you have installed SuperMOOC 1 at LRZ, we organized study tour from a group of us from Singapore, who were incredibly impressed with what you have done there. And of course also Aquasar and work at IBM and then SuperMOOC. And that's why later in the specs for the first supercomputer, petascale supercomputer in Singapore, Aspire 1, we have specified that we definitely insist on hot water cooling, which forced many suppliers, integrators, and suppliers of HPC equipment to very quickly review their plans. And indeed, Fujitsu immediately bought a very large supply of cooling elements from this Danish company, whatever it's called. So that's you have had a direct impact on how things developed in other parts of the world. And Singapore is a tropical, equatorial country, so cooling is super important. So now I don't see questions yet. Oh yes, here there are a few questions now. 3. Sagar Dollars, what do you think is next big innovation in terms of energy efficiency? Compute plus memory, architectures, cooling technologies.
So the next, can you repeat the question?
What do you think is the next big innovation in terms of energy efficiency?
Ah, okay. The next big innovation, that's a hard question. So concerning cooling efficiency, I've already mentioned the next big innovation will be completely direct liquid cooled racks, where all components of one rack, of each rack, are direct liquid cooled, so you can thermally isolate them. Concerning compute, yeah, it might take 5 to 6 years, but then quantum computing or a quantum computer accelerator might improve the time to solution for quite a large number of applications. But you know, quantum computers, you cannot cool them with hot water. They need very, very cold. They need cryostats to be operated.
Right. So we have a few more questions. Henry Strauss is asking, how much more expensive is your liquid cooling solution compared to an air-cooled one? How does this compare to the energy savings?
For a large system, I would say the price add-on is in the order of 5%. And so, you know, in Germany, the electrical bills are really, really expensive. We have to pay 18.5 euro cents per kilowatt hour. And I've already mentioned the savings. The annual savings for direct liquid cooling are in the order of millions.
Yes.
So within 1 or 2 years of operation, the add-on price is really, you're on the safe side. You're on the you gain, you save money.
So here's another question from Joshua O. Has the team considered liquid immersion cooling of the compute versus direct cooling into chip?
I've visited 2 data centers which use liquid immersion cooling, and I'm no fan of it. Yeah. So if you use oil, mineral oil, so the oil creeps along all cables. Yes. So yeah, it's really hard to keep the room oil-free. And if you use other components, they are first very expensive, and if they are released to room air, they have a large heat potential for the Earth. So I'm really no fan of that.
Right. We may add that there was a very large scale demo, which is Tsubame KFC, built by Satoshi Matsuoka. That's a lesson learned. There were also several attempts to have not only immersion but also phase change immersion using 3M of Novak and various other. But Novak is extremely expensive, and it's locked, and you lock yourself into one supplier. So that's water is everywhere. So water is the cheapest cooling material medium you can ever imagine.
And it's very efficient.
And it's efficient enough, as you have demonstrated, to be the first choice. And there's a final question: how does the weather, winter versus summer, affect operation of the machines?
It does not affect it at all.
Right.
We can winter the whole year long. We operated the machine without any chillers, so there is no effect. In summertime, we increase the inlet temperature up to 45 degrees Celsius, so you don't need any chiller to get 45 degrees Celsius water from our cooling towers.
Herbert, thank you very much.